Now we have one of the more important theorems from the chapter, actually from the book in general. So this one says that all n-dimensional vector spaces are isomorphic. Or more precisely, if we have two vector spaces, they're isomorphic if and only if their dimensions are equal. So let's say two finite dimensional vector spaces are isomorphic if and only if they have the same dimension. Okay. Proof. So we've got an if and only if. So let's do the forward direction first. So for this one, we'll be assuming that we've got two finite dimensional vector spaces that are isomorphic. So suppose that V is isomorphic to W and that they're both finite dimensional. Then that means we can introduce a map and start talking about things in terms of the map. So it's one thing to say that V and W are isomorphic. It's even better to say that there's an isomorphism T between the two of them from a proof writing standpoint, because now we can talk about things in terms of T. So since T is invertible, what do we know? Well, we know that it's injective, which means that the null space of T is 0. And we know that it's surjective, which means that the range of T is all of W, right? And now we can just plug this into the rank nullity theorem. So then we have that the dimension of V is equal to rank T plus nullity T, which from the previous line we see is, so the dimension of the range is actually just the dimension of W, and the nullity is just 0. And so, oh, look at that. The dimension of V is equal to the dimension of W. So we're using rank nullity. That's 322. Okay, and now we need to go in the other direction. So for the other direction, we're going to be assuming that they have the same dimension. So suppose we have two vector spaces of the same dimension. So the dimension of V and the dimension of W are both equal to n. Okay, so then if we know something about the dimension, then we know something about how big the basis is for each of these. So there's a basis V1 through Vn. Oh, I missed a word. There are bases V1 through Vn of V and W1 through Wn, same subscript for W. So yeah, so just maybe emphasize that that's the same n in both places. Okay, and then let's see. So now we're trying to show that they're isomorphic. Well, one way to show that they're isomorphic is to cough up an isomorphism, and if you think about it for half a second, you'll probably remember something that we talked about very recently, and that is where we just define sending a linear combination of the VJs to the same linear combination, meaning same coefficient, but we just brutally swap out the basis vectors now with WJs. And this defines a linear map by 3.5. It remains to check that it's invertible in order to know that it's an isomorphism. So again, we'll do the two parts, the injective part and the surjective part. So since W1 through Wn is independent, it must be the case that the null space of T has nothing but 0 in it. Whence we can say that T is injective. Meanwhile, since W1 through Wn is a spanning set for W, T is surjective. Therefore, T is an isomorphism. And we are done with both directions.